Hi students, welcome to Science Extension and Module 3, the Data, Evidence and Decisions. This is video number 8. We're going to talk a little bit about some of the errors that could arise in practical investigations. The specific learning outcome that I'm trying to address in this video and that you will need to try and think about is that you can apply appropriate performance measures to the statistical analysis of quantitative data sets obtained from conducting a relevant practical investigation, including but not limited to error. So this is part of a little series that we're going to be looking at in terms of carrying out practical investigations and some of the things to be looking out for as you do this. So in this case, we're going to talk a little bit about errors. And errors in practical investigations are the difference between the measured value and the true value. Now, this concept of true value is important because it's often theoretical values, what we would expect if conditions were ideal. And of course, that doesn't always happen. And in experimental procedures, it's very difficult sometimes to be able to control absolutely every variable and hence to be able to get to the exact value of what something would really be. And what that means is that there's always going to be some source of error. There's going to be some discrepancy between the values that we measure in the experiment and the actual true values. That said, there are two types of errors that we need to look out for, and they are systematic errors and random errors. Systematic errors are consistent and predictable errors. These are ones that we should be able to identify and potentially eliminate from our experimental procedures. Random errors are unpredictable fluctuations, things that maybe just happen that you weren't thinking about, that you didn't realize may have had an impact on your results. And sometimes it's not until we get through and have to look back that we see where some of these errors have actually come from. So we'll talk about each of these in a little bit of detail and how they might relate to practical investigations in this video. So firstly, let's talk about systematic errors. And systematic errors, as I said, are consistent and predictable errors. The good thing about them is they're often easily corrected. And this means that if we can identify a systematic error, then we can often make a correction that is going to address some of that potential discrepancy between the values that we're recording and the true values. Some procedural things would fall into the systematic errors. So when you're using an electronic balance, remembering to tar it first. Or if you're using a pH meter, to use buffer solutions to actually check that the meter is reading the correct values. So often that will be dependent on what types of values you're looking at. If you're looking at acid solutions, for example, you might calibrate your pH meter against a pH of 4 and a pH of 7. If you're going to be trying to look at the entire range of values, you might calibrate a pH of 4 and a pH of 10, for example, just to make sure that your meter is reading the correct values as you go along. If they're slightly out, say they're slightly out by 1, that means all of your values, all of your measured pH values are all going to be 1 too high or 1 too low. And that's what we mean by systematic errors. You're doing the same thing consistently. They're all wrong, but they're all consistently wrong. So they may be all out by 1 pH. So therefore, if we can identify that, if we can correct that, maybe recalibrate our instruments, then retake the measures, what we might be able to do then is say, well, I'm going to ignore that first set of values. Now, it might seem like we're ignoring data, but if we have a systematic error, we need to be able to correct for that sort of an error. And that's one of the reasons why we do this sort of procedure. Likewise, if you either haven't been taught correctly or if you're lazy and you don't take the time to bend down, make sure that you're reading scales for volumes, for example, at eye level, then you can introduce that idea of parallax error, that sort of shifting where you're looking at something not straight on, you see a slight angle in your reading. And of course, that's usually demonstrated by holding one finger out in front of you, close one eye, and line it up with something on the far side of the room, and then close the open eye and open the closed eye, and it looks like your finger has moved relative to the background. And that's what parallax error is. It's just looking at something from a slightly different angle and creating a slightly different value. And again, it's easily corrected because we just say, well, don't read the scales like that. Make sure you're reading them straight on. Make sure you're looking at, say, the bottom of the meniscus, that sort of thing. Each of these little things are systematic errors. They're errors which I suppose we could call human error in one sense, but they are correctable. So they are things that we can think about how we might be able to eliminate these errors as much as possible from what we're doing. There's another concept called instrument drift. This is particularly so if you use electronic devices, if you're using electric circuits, for example, and you're measuring voltages and currents and things like that, sometimes as instruments are warming up, they can slightly change their resistance. And if they slightly change their resistance, then that might also change their values. So if you're taking measurements over a short period of time, this probably won't have a big effect on your values. If you were taking measurements over the course of a day, for example, you might find that there is a little bit of instrument drift that is actually slightly changing some of these values as the instrument itself heats up or cools down, and even just taking values with an instrument in summer versus winter can have these sorts of little impacts. So these are some of the types of systematic errors to consider and also to try as much as possible to eliminate. And random errors are a little bit trickier because they are unpredictable fluctuations which can be challenging to detect and or control. So these are some of the things that might find their way into your results, and then afterwards you're going to have to try and think about, okay, what am I going to do about these? Am I going to have to repeat an experiment? Is there some way I can account for these sorts of errors? So sometimes just people moving around in a room, drafts that might be allowing air to come into a process. Maybe that's just affecting your measurements, your weight of particular samples on an electronic balance. There might be changes in room temperature, particularly if you're looking at carrying out an experiment over several months, for example. Light and dark differences. Sometimes rooms are made darker if a group of physicists are in there doing an experiment on light or waves. Other times there might be a lot more light in. Maybe again that's related to the different times of the year. And electrical or magnetic noises, interference patterns. There's all sorts of different things which may be having an impact on your results that you're not entirely aware of. Physical errors based on the heterogeneity of different samples. And this is one of the reasons why we do things like repetition. If, for example, we were carrying out an experiment to heat up a rock and then cool it down again in order to determine the rate of mass lost through physical weathering processes, for example, and even with the same type of rock, some slightly different samples might behave slightly differently during the experiment. We try and avoid this kind of error by repetition, by doing multiple samples and trying to overcome those individual ones. This is particularly true for biological experiments with growing seeds or plants. There may be some idiosyncratic things about different plants that make them grow better or not as well or respond in different ways. And so a larger sample size often tries to account for any of these individual differences. The resolution and choice of instruments is important. Sometimes this is going to be linking into accuracy, and it's a classic case of measuring volume with a beaker, for example, as opposed to a measuring cylinder or a graduated pipette. There are different devices and different instruments, different apparatus that we use in science for different purposes, and each of them has associated with them, I guess, the ideal situations for them to be used. Certainly, it should always be a consideration that you are using the best available instrument that you have for the particular purpose that you are after. One final one, which can be, I guess, a little bit trickier, but is a source of random error, is incomplete definition. So this is where people are individuals. We don't always agree on everything. And sometimes when two people are taking measurements or two people are trying to work through a particular process, determine an endpoint, for example. This could be something simple as color change during a titration, or if you've got a piece of elastic device, a string or rubber band or something, and you're trying to measure something without stretching it, at what point are you kind of pulling it out and not stretching it or not counting it as stretching? And if your definition differs to me, then we have incomplete definition. Then we have a situation where we're both interpreting something slightly different ways. And if it's a titration, for example, we're looking for that very faint pink color as the indicator of the end point of the titration, and you and I decided slightly differently, this can be a source of random error, particularly if you're doing some titrations, I'm doing some titrations, we're working through the processes together. We might end up with a slightly different set of results for the ones that you've been working on to the ones that I've been working on. So that's where it's important, if you're working with a partner or partners, to really make sure that you're clear about exactly what you're looking for, when you're going to stop a particular experiment, what sort of values are specifically trying to measure, to what level of decimal place are you working at, All of those sorts of things can be really important and can link into this area of random error. Another way of trying to reflect some of the error that can occur in experiments is to use these error bars. So when we're talking about graphing our results, sometimes we can reflect some of the perceived error that we have in our data by using these error bars. So by saying there's actually a range in which I feel these results are sitting, and so therefore when we draw our line of best fit, we're kind of drawing that line between that range of values rather than just trying to simply pass through each of the data points individually. So this is another way of representing the types of things that we can sometimes see in our graphing of a set of results. And what I want to try and do is to start to tie in this idea of errors to our statistical testing, which is what we're going to be coming up with very, very soon. Because there's another way to think about errors, and that is in relation to our hypothesis. Specifically, it's about whether or not we accept or reject our hypothesis. So we're going to talk about the sorts of hypotheses that we usually talk about, which is that I think there's a relationship between the X variable and the Y variable, such as the X variable increases, the Y variable increases, for example. We're also going to be talking about what we call null hypotheses. And a null hypothesis is nothing, no relationship between them. So on what basis are we looking at accepting or rejecting hypotheses, and what sort of errors might be associated with this? Well, one of the ways to help you think about this is to think about what might happen during a criminal trial. So during a criminal trial, somebody may be accused of a particular crime. Now, what we would like to do is, if there's an innocent person, that we would find them innocent, or if there's a guilty person, that there would be sufficient evidence that we would determine their guilt. What we don't want to do is we don't want to convict an innocent person. Likewise, we don't want to send a guilty person out with lack of evidence. So possibly you might have a view about which one of those would be preferred. Perhaps we would prefer that a guilty person goes free rather than an innocent person was actually convicted. It all depends on your perspective. But what we've got is two different types of errors that are associated with these two false conclusions, if you like. So this is less about the evidence and more about how we use the data as evidence in support or to reject our hypothesis. Remember that the null hypothesis is no relationship, nothing. So the first type that we want to have a look at is when we reject a null hypothesis when it's actually true. So there's no relationship here, but we reject it because we think there is one. Okay, that's what we call a false positive. Analogy would be that we convict an innocent person. We find there is something there when actually there wasn't. This is called alpha. And one of the things that we want to try and do is we really want to try and minimize this. And this is one of the reasons why we set such a low value when we're looking at our statistical testing, because we don't want false positives. We don't want to conclude that there's a relationship. We don't want to reject the null hypothesis unless we've got really good reasons for doing so. The type 2 error is the alternative, which is that we fail to reject a null hypothesis when it's actually false. There is something going on, we just didn't find enough evidence to suggest that it was. So that's failing to convict a guilty person in our analogy. It's a false negative. There is actually something going on here. We just didn't find it. What we feel is more important, of course, is that we don't want to convict an innocent person. We don't want someone to go to jail if they haven't done anything wrong. And we don't want to be rejecting our null hypothesis when there is actually no relationship. We don't want to assume relationships exist when there are none. And so what we do is we're trying to focus on our type 1 error. We're trying to minimize the chances of a type 1 error. Now, one of the problems that we have with type 1 and type 2 errors is that when you tighten control for one, you lose some control of the other. So if you are really making sure that there is absolutely no way that you could possibly convict an innocent person, then that would create a very high burden of proof that you would have to have lots and lots of evidence in order to convict someone. And so as a result of that, it's possible that you might not have sufficient evidence to convict someone who was actually guilty. And this is the problem with these types of errors, is when you tighten one up, you can actually allow the second type to be a little bit more common. So we're going to focus on the null hypothesis. We're going to focus on accepting or rejecting it. Now, if we accept it and it's true, then that's fine. But if we reject it and it's true, then that's the sort of thing that we want to try and avoid. To do this, we look at this alpha level. So we look at this type 1 type of value or conclusion that lets us have some confidence in our conclusions. And the standard level that we set this to is the 5% significance level. So basically, there's a 1 in 20 chance that we're going to be convicting an innocent person. Now, of course, you may find, depending on the stakes, if you're using something where you're looking for the relationship between, say, a particular medication and a disease, you might want an even tighter one. So you might go down to 0.01 or perhaps even 0.005. These can change, and often they are associated with the type of test that you're looking at. But overall, the focus on what we're trying to do is to minimize our chances of making a type 1 error. And to do that, we've set this alpha level, we've set the value that we're going to require of all of our procedures to be at a maximum, if you like, of a 0.05 level. It's got to be below that. If it isn't, then we're going to accept that there is no relationship and the null hypothesis is actually true. So this is a bit of an overview of some of these different types of errors that can be associated with practical investigations, and also some of the conclusions that you will draw from the results of these investigations. Thanks for watching.